Okay, so now that everybody's logged in and we've completed our sound check, let's begin with today's webinar. So welcome everybody. Thank you for being on time, those of you in attendance. This is going to be the fourth webinar in the series of GCSE Physics webinars for 2019. This one is on the subject of atomic structure, radioactivity, and fission and fusion. In keeping with the format of the previous webinars in this series, we're going to start for the first hour with going through the topic teaching, the key ideas. We're going to then have a 5-minute break. After that, we're going to go into the second hour of the webinar, which, depending on how you all vote during the 5-minute break, will be either continuing with the topic teaching or we're going to go through the exam questions, which again you all received in your exam question pack. So you would have received a PDF of this document over here. If you need to find the resources page for this webinar, again, those of you who booked tickets, you can just go to the first page of your exam questions pack and click on this link here. That will take you to the private page that you will have access to, where you will find the resources for this webinar within about 48 hours of today. You'll also be able to continue to ask me questions and discuss this topic with me to assist your revision all the way up to the end of your exam period in late June. Let's begin with some basic ideas here. So your specifications will typically, depending on which exam board you're studying for, will begin with an overview of the history of the development of the atomic model. Now, the idea of an atom actually comes from ancient Greek philosophy. Now, this is something that we actually covered in a previous webinar for GCSE chemistry students, but we'll review it briefly here. So the ancient Greeks, before what we describe as modern science began, they engaged in philosophical discussions and arguments with each other in order to determine the nature of things. One of these discussions was about the nature of matter, the nature of physical materials. And one group of ancient Greek philosophers believed that matter was continuous, that you could continue to divide matter into smaller and smaller pieces, effectively forever, getting smaller and smaller pieces as you went along with each division. But there was another group of ancient Greek philosophers who thought otherwise. They thought that there was a particle of matter that was so small that it couldn't be divided any further. So the word atomos comes from the ancient Greek for the uncuttable or the indivisible one. And it was this group of ancient Greek philosophers led by Democritus who essentially formulated the first idea of the atom. Now, in modern times, it was actually John Dalton who gave us the first working definition of an atom, and he kind of went along the same lines as the ancient Greeks in the sense that he believed an atom to be a tiny piece of matter which was indivisible. But Dalton's conception of the atom was that it had no internal structure. Now, the definition for the term chemical element also comes from this idea. So in 1806, he defined the chemical elements as being substances composed of only one type of atom. And so this is very much the same definition that many of you will find in your exam board specifications for GCSE chemistry. He conceptualized the atom as being a featureless particle with no internal structure, kind of like a solid ball. And now, again, we define an element as being composed of only one type of atom, and an atom as being the smallest particle that comprises a chemical element. And so John Dalton's idea of an atom was very much similar to that of the ancient Greeks, the Democritan philosophers. But he took it slightly further by saying that the different chemical elements, the simplest chemical substances that can exist, are each made of a different kind of atom. So the next person to develop the idea of atomic theory in the history of science was J.J. Thomson, and in 1897 he showed that an atom contained small negatively charged particles within it. So he progressed the idea of an atom beyond John Dalton's idea of a featureless sphere with no internal structure. He said, yes, an atom actually does have internal structure, and he showed by experiment that the atoms themselves contained even smaller negatively charged particles. So he coined the term electron to describe these particles, but he also knew that atoms were electrically neutral overall, and so if they had these small negatively charged particles within them, it followed that the remainder of the matter that made up the atom, within which these small negatively charged electrons were embedded, must have been positively charged, so that the positive charge exactly balanced the negative charges of the electrons to give an electrically neutral atom. So this gave rise to a model of the atom that became known as the plum pudding model, where the atom was made up of a sphere of positively charged material within which you have these negatively charged electrons embedded, kind of like plums in a plum pudding. And so this is where we get the idea of the plum pudding model. So the next scientist who developed the idea of atoms further was Ernest Rutherford. Now in 1910, he and his team of scientists carried out a series of experiments where they fired alpha particles at a very thin sheet of gold film. Now Rutherford expected all of these alpha particles to pass straight through the gold film, but in fact he found something else was happening. So this is a kind of very simplified diagram to show Rutherford's experiments. So here we have the very thin sheet of gold film, and he fired alpha particles at this sheet of gold film and then detected which directions those alpha particles were moving in once they hit the gold film using a piece of photographic film positioned like this. And wherever the alpha particles hit this photographic film, they discolored the film, and this showed that to Rutherford that the alpha particles were being deflected. Some of them were passing straight through, but many of them were being deflected at different angles as they passed through this sheet of gold film. And so from this observation he proposed that the atom is mainly empty space, but the majority of the mass, the majority of the matter that makes up the atom is concentrated in a small, dense, positively charged nucleus around which the negatively charged electrons were orbiting. And so again we see that Rutherford's experiments further elaborated our model, our understanding of the atom. Now to illustrate this a little bit further, I like to use one of these simulations from the PHET website. I can thoroughly recommend this website to find physics and chemistry, and also some biological simulations that you can play around with and discover some of, better learn some of the aspects of these different ideas in science. So we have here the Rutherfordian model of the atom and the plum pudding model. Now the plum pudding model again was the idea that an atom is made up of a positively charged piece of material within which you have these negatively charged electrons embedded within it. So when you fire alpha particles at this, you would expect to see a very different result from what Rutherford saw. So this is the same experiment with a sheet of gold film and a source of alpha particles being fired at the gold film. Now alpha particles are composed of 2 protons and 2 neutrons each, and so they are essentially the same as a helium nucleus. So the nucleus of a helium atom has 2 protons and 2 neutrons, and so an alpha particle is essentially the same as the nucleus of a helium atom. So given that the alpha particles are positively charged, when you fire them at atoms, the reason Rutherford saw the scattering of those alpha particles at various angles was because some of the alpha particles will pass near enough to the nuclei to be electrostatically repelled from them and then deflected through these various angles, whereas others will pass straight through the empty space around those nuclei. And so this explains the observations that Rutherford made. So if we zoom in on one of these nuclei, we can see what's happening in a little bit more detail here. So the nucleus, being composed of positive charges and neutral particles, the neutrons, itself has an electrostatic field around it, and this electric field will repel other positively charged particles like alpha particles, and the closer they get to the object causing the field, the nucleus, the bigger the force acting on those particles to repel them away from the positively charged nucleus, and therefore the greater the deflection that those alpha particles will experience. The further away they are, the less deflection they will experience as they move through that piece of very thin gold film. And so Rutherford's model of the atom was intended to explain why the alpha particles didn't all just pass through the atom, but that they were deflected at these various angles, and some of them were even reflected backwards away from the gold film as well. So, now the next big jump in our understanding of the structure of the atom came with the work of another scientist in the early 1930s, Niels Bohr. Now, Niels Bohr was important for a number of reasons. His work actually led, among other people's, other scientists' work, to the development of quantum theory as well. But on the basis of Rutherford's experiments and Rutherford's theories, he proposed a new model of atomic structure where the atom, again, consists of a very small positively charged nucleus around which the electrons are orbiting, but he elaborated the model a little bit further to say that the electrons don't just move around in random orbits, they actually move around at concentric energy levels at specific distances from the nucleus, with the lowest energy levels being nearest the nucleus and the highest energy levels being the ones furthest away from the nucleus. And so Niels Bohr again took the model of the atom further, and all of this was done on the basis of a series of experiments that he did. Now, the next big jump in our understanding of the structure of the atom came with the work of another scientist, James Chadwick. Now, he was assigned the task of tracking down evidence of Rutherford's tightly bound proton-electron pair. Now, at the time that Rutherford was doing his experiments, he didn't know that the particles in the nucleus which were neutral were discrete particles called neutrons. He thought of them as being a pair of particles, a proton and an electron, within the nucleus, which gave that overall pair a neutral charge. But in 1930, it was discovered that beryllium, so let's show you the position of beryllium on the periodic table here. So it was discovered that this element, when it was bombarded by alpha particles, gave off a very energetic stream of radiation. And so at first, this was thought to be gamma radiation until there were further experiments done that determined it was in fact made up of a stream of particles, not waves like gamma waves, and these particles each had the same mass as a proton, but no electrical charge. And so he was awarded the Nobel Prize for his work, which led to the discovery of the neutron. So, today scientists accept that an atom has a small central nucleus which occupies a very tiny proportion of the volume of the atom, and that the electrons orbit the nucleus at different energy levels, at different distances from the nucleus, and that the nucleus itself is composed of two types of particles, neutrons and protons. So there have been many different models of the atomic structure, and there continue to be elaborations on these models. So in this model here, which resembles many of the kind of diagrams that you'll see in textbooks, the dot and cross diagrams that you've perhaps seen in GCSE chemistry, the model of the atom being shown here, it does give you a sense of what we've been talking about. You have a very small central nucleus within which you have the protons and the neutrons. You have the electrons orbiting in concentric energy levels at specific distances from the nucleus, but this model has its limitations, first of which is the fact that it represents the atom as being a two-dimensional object. The important thing is to remember that an atom is a three-dimensional object, and that the electrons are in fact moving around the nucleus in 3 dimensions. But those of you who go on to study physics at a higher level, perhaps A level or higher than that, you'll realize that electrons can also be modeled not as particles but as waves. And so another model of the atomic structure would give you an idea that electrons are not particles that move in concentric energy levels, but standing waves which transfer energy around the nucleus at specific distances. But this is typical of science in the sense that we start with a certain model, we do experiments, we develop that model further on the basis of the observations that we're making as they either confirm or refute our hypotheses. So the nucleus is often thought of, particularly by students at GCSE level, as being somehow static, that it's not moving. But in fact, the nucleus itself contains particles, the protons and the neutrons, which are themselves in a constant state of motion. Now, the nucleus of an atom is very, very small compared to the volume occupied by the electrons of the atom in their motions. So a lot of analogies are used to give you an idea of just how small the nucleus is compared to the size of the atom. So for example, if an atom could be enlarged to be the size of a football stadium, the nucleus of that atom would be about the size of a golf ball, somewhere above the center spot in that stadium. So again, one of the simulations that I like to use in this context to illustrate the relative sizes of these things is this one here. It's a very interesting simulation called the Scale of the Universe, which you can find on Google. So, for example, if we take the average size of a human body, 1.7 meters, and then scroll into this model to see the relative sizes of smaller objects, we would have to go down to a very fine level of detail, a very small scale, before we get to the objects the size of atoms. So now that we're at the nanometer scale, 10 to the power minus 9 meters, we start to see some atoms here. So we can see here a cesium atom. So a cesium atom is 500 picometers, 5 times 10 to the power minus 10 meters. Carbon atom is 340 picometers, a water molecule 280 picometers. And so when we come down to the size of a hydrogen atom, we start to see just how small some of these particles can get. And of course we can even go smaller to a uranium nucleus, femtometers. Now femtometers is a measure in the 10 to the power minus 15 of a meter. So 15 femtometers would be 1.5 times 10 to the power minus 14 of a meter. If we want to see how small a helium nucleus is, 3 femtometers. So protons and neutrons, 1 femtometer, 1 times 10 to the power minus 15 of a meter. And of course we could even go smaller, but when we start to look at things like quarks, the sizes of these things have yet to be confirmed by experiment. So I'd encourage you guys to have a play around with this simulation, and also we're probably likely to see this simulation again in this webinar series, because it does also allow you to look at very large objects. So you can also look at things on the scale of planetary bodies, stars, clusters, and so on. So again, do have a play around with this simulation. It is very, very interesting. So now an electron is even smaller still. So we saw that a proton or a neutron is about 1 femtometer in size, and the masses of these things, protons, neutrons, and so on, are not measured usually in standard units of mass, which would be kilograms, because while we do know the mass of a proton or a neutron in kilograms, it's not a very useful number because it's an incredibly small number when expressed in kilograms. So the masses of these types of subatomic particles are usually expressed in atomic mass units. So if a proton or a neutron each have 1 atomic mass unit, an electron is roughly 1,840th of that mass. So about 1/2000th the mass of a neutron or a proton. So electrons, the mass of an electron is usually considered to be negligible. In other words, to have a mass so small that for all intents and purposes it is effectively massless. It doesn't really contribute anything significant to the overall mass of an atom. And so this is why we say that the vast majority of the mass that makes up an atom is found in the nucleus, in those protons and neutrons. Now the electrons again can be modelled as either particles or waves, but in either case they are moving extremely quickly. So the electrons orbit so fast around the nuclei in those concentric energy levels that they effectively form shells of negative charge which are arranged around the nucleus. Now the electrons will occupy the shells starting from the lowest energy level, the one nearest the nucleus, outwards. And each shell, as you saw in GCSE chemistry, each shell has a maximum number of electrons that it can hold. So protons, neutrons, electrons, these are all types of subatomic particles. Protons and electrons are electrically charged, which affects the structure and the stability of an atom. And so if we imagine comparing the relative charges, the relative masses of these 3 types of subatomic particles, you should have an idea of these numbers. So once again, we're not measuring the mass of these particles in standard units, which would be kilograms, and for the same reason as we don't measure the mass of these particles in kilograms, we also don't measure the charges of these particles in the standard units of charge, which would be coulombs. Instead, we use relative charges, comparing the charge of a proton to that of an electron and vice versa. So neutrons have no overall charge, they are electrically neutral. Protons have 1 unit of positive charge, and electrons have the same amount of charge, but it's negative. And the relative masses of the proton and the neutron and the electron we discussed earlier on. So, an uncombined, unbonded atom is a particle which contains an equal number of protons and electrons, and for this reason, atoms are electrically neutral until they lose or gain electrons. So all substances on Earth and elsewhere are built from atoms which contain those 3 subatomic particles. Now the elements of the periodic table differ from each other in that their atoms contain different numbers of these subatomic particles. The elements in the periodic table are arranged in terms of increasing atomic number of their atoms. In other words, the number of protons. So the number of protons in a particular atom is called its atomic number, and this is what determines which element that atom belongs to, the identity of that element. So for example, all lithium atoms have 3 protons because the atomic number of lithium is 3. All carbon atoms have 6 protons. All uranium atoms have 92 protons. So we mentioned that the mass of an atom is mainly found in the nucleus. Protons and neutrons have approximately equal mass of 1 atomic mass unit, and the mass of an electron is negligible. So for example, carbon atoms that have 6 protons and 6 neutrons have an atomic mass of 12 atomic mass units, and so the atomic mass of a carbon-12 atom, or the mass number as it's called, is 12. Now, many of you were asking me to talk about the topic of isotopes when you were voting for the topics to be covered on the private webinar page prior to this event. So let's take a look at the concept of an isotope. So, as I've just said, the atoms of a particular element belong to that element by virtue of their unique atomic number. And so all atoms of the same element have the same number of protons in their nuclei, but atoms of the same element may have different numbers of neutrons. And so there may be atoms of the same element that have different mass numbers. So these are called isotopes of that element. So for example, within a sample of oxygen atoms, some of those atoms can have either 8, 9 or 10 neutrons, even though they all have the number of protons unique to oxygen atoms, which is 8. So we have oxygen 16, we have oxygen 17, and we have oxygen 18, the 3 isotopes of oxygen. So you can see here, they are all oxygen atoms because they all have the same atomic number, but they all have different mass numbers because they have different numbers of neutrons. So carbon-12 is the isotope which gives the against which the mass of other atoms is compared to give the relative masses of those elements. So the most common isotope of carbon is in fact carbon-12, and again this can be represented like this. So a carbon-12 atom has 6 protons, which is the same for any isotope of carbon, but this particular isotope has 6 neutrons, and if it's an atom, it will also have an equal number of electrons to protons, which will be 6. And so this diagram would represent a diagram of a carbon atom. Now there are other isotopes of carbon, so one of these is carbon-14. So carbon-14 would be represented like this. And so a carbon-14 atom also has 6 protons because it is a carbon atom, and the atomic number, which is unique to carbon atoms, is 6. But the mass number of this isotope tells us that with these 6 protons, we also have 8 neutrons. Now again, in an uncombined, unbonded atom of carbon-14, you would have the same number of protons as electrons, and so this atom would also have 6 electrons. So this diagram would represent an atom of the carbon-14 isotope. So the isotopes of atoms correspond to atoms of the same element which have different numbers of neutrons, and so this is what gives rise to the definition of relative atomic mass versus atomic, the mass number. There is a difference between mass number and relative atomic mass. So for example, the relative atomic mass that appears in the periodic tables that you're probably familiar with for GCSE students, both for chemistry and for physics students, would be 35.5 or thereabout for the relative atomic mass of chlorine. Now this periodic table displays the relative atomic masses in the bottom left of these squares, but that doesn't really matter. You can always tell that, which of these numbers is the atomic number and which of these numbers is the relative atomic mass, because the atomic number always goes up by 1 as you go from left to right across a period, a horizontal row of the periodic table. So chlorine on the periodic table has a relative atomic mass of 35.5, but the reason for this is because the term relative atomic mass describes the weighted average of the mass numbers, the masses of the isotopes of that element compared to 1/12 of the mass of a carbon-12 atom. So if we look at the isotopes of carbon-12, carbon-12, the most common one, we can see here the percentage abundance of carbon-12 is 98.93. So 98.93% of all naturally occurring carbon atoms are of this isotope, carbon-12. The remainder are carbon-13 and carbon-14 atoms. Now, in the 1960s, scientists met to decide which of these elements would be the standard against which the atomic masses of the other elements would be compared. So, seeing as the carbon-12, an atom of carbon-12 has 12 atomic mass units, 6 protons and 6 neutrons, 1/12 of a carbon-12 atom, the mass of 1/12 of a carbon-12 atom in kilograms would correspond exactly to 1 atomic mass unit. And so they chose the carbon-12 atom as the basis for the relative scale of atomic masses. Now they could have chosen other elements. They kind of chose carbon mainly because it's an important element in the sense that it's the basis of all life on Earth. So 1/12 of a carbon-12 atom's mass in kilograms corresponds to 1 atomic mass unit. And so, if we take chlorine, for example, chlorine has 3 isotopes. By far the most common is chlorine-35. There are also chlorine-36 and chlorine-37 atoms, but chlorine-35 makes up about 75.78% of all chlorine atoms. The chlorine-37 atoms are the next most abundant isotope. Chlorine-36 exists in very tiny quantities and it's almost negligible. And so the relative atomic mass of chlorine would be the average mass of the isotopes, but it would be the average weighted according to the percentage abundance of those isotopes. So for example, if we wanted to calculate the relative atomic mass of chlorine, we would need to take into account not just the mass numbers of the atoms of its isotopes, but also their relative abundances. And so the way that this is done is you would take the mass number of the isotope. So we're not going to count chlorine-36 because it's negligible abundance. Let's just take a look at chlorine-37 and chlorine-35. So chlorine-35 is present in an abundance of 75.78. So we would take that, 35, multiply it by its percentage abundance, 75.78. And then we add that to chlorine-37. So we take the mass number, 37, multiply it by its percentage abundance, 24.22. And we then divide this by 100 to get the relative atomic mass, which is 35.5 or thereabouts. And so this is how relative atomic mass is calculated. Now I say this because a lot of the time, one of the common mistakes that I see with students is that they confuse mass number with relative atomic mass. Mass number, as you can see here, the mass numbers of these isotopes, they're all whole numbers because they describe the total number of units of mass which makes up an atom of each of these isotopes. And you can't have fractional mass numbers because the mass number is obtained by adding up the numbers of protons and neutrons, each of which has 1 atomic mass unit. But the relative atomic mass can be fractional, it can be a decimal, and it is because of the fact that it's a weighted average of the relative atomic of the mass numbers of the individual isotopes. So there is a difference between mass number and relative atomic mass. Just bear that in mind and don't confuse the two because students do lose marks for that. So now that we've taken a quick review of atomic structure, let's now move on to the idea of radiation and radioactivity. Now, the word radiation is a very general word. It simply means the emission of energy in the form of waves or particles from an object. So the word radiation on its own is a very general word. It can also be used to describe the emission of heat from a hot object to a colder surroundings. But in this context, we're talking about nuclear radiation, radiation which is given off by unstable nuclei of certain elements. So what do we mean by the term radioactivity? Well, isotopes, such as carbon-14, are not stable. Some isotopes of some elements are considered to be unstable. So these types of isotopes, these unstable isotopes, will give off excess energy in the form of either particles or waves. So this is what we call radioactivity. Now, the the emission of a particle such as an alpha or beta particle or a gamma wave is called radioactive emission, but specifically when a particle is emitted from a nucleus which is unstable, this is sometimes called radioactive decay, and the change that occurs in that nucleus is called a decay reaction. So a decay reaction occurs because that nucleus is in an unstable state. It has an excess of potential energy, nuclear potential energy. And so by giving off the excess potential energy, it can leave behind a more stable nucleus. Now, this is accompanied also by the emission of heat energy as well. So the idea of stability versus instability is a little bit of a tricky one for GCSE students because, again, as I've said before in these webinars, particularly in GCSE chemistry, where we encounter the idea of stability and instability as well, the term stable, when it's applied to atoms or nuclei, really describes a state of high potential energy. So if we're talking about an unstable nucleus, what we're really saying is that we have a system which starts in a state of high potential energy. So if we imagine we have, let me draw a slightly better vertical line here. Okay, so let's imagine we are considering the amount of energy present in a system which contains a single nucleus. So let's say we have an unstable nucleus here. So here we have an unstable nucleus. So the term unstable in this context describes a state of high potential energy. So this is our potential energy level. And this is what we mean when we say a nucleus is unstable. Now, we'll talk about the reasons for instability shortly, but if we have an unstable nucleus, it can achieve a more stable condition by giving off the energy difference between the unstable condition and the more stable condition. And so by going from here to here, we are going from a high potential energy condition to a lower potential energy condition. But energy is conserved. You can't start with this level of energy and end with this level of energy by just making that energy disappear. The energy has to go somewhere. So when this occurs, when this change occurs from an unstable nucleus to a stable nucleus, the energy difference, which we can call delta E, this energy difference has to go somewhere. So as I said to you guys before when we spoke about energy in the second webinar of this GCSE Physics series, we said that the energy of a system can be described in terms of the sum of the potential and the kinetic energy of that system. So if we imagine that this nucleus starts in a state of high potential energy and ends in a state of low potential energy, the total energy of the system must be the same. And so where is this energy difference gone? Well, the energy difference can either be given off as a wave, so this would be a gamma wave, and a wave transfers energy. Now again, we'll cover waves in a later webinar in this GCSE Physics series, but waves, electromagnetic waves like gamma waves, do transfer energy. The energy carried by a wave, let me just got so many applications open, things are lagging a little bit here, sorry about that. So the energy carried by this wave is going to be equal to a constant called Planck's constant multiplied by the frequency. So this energy that's carried by this wave is going to be equal to this energy difference between the stable state of this nucleus and the unstable state of the nucleus, if the gamma wave is the only wave being given off. So the energy carried by an electromagnetic wave is proportional to its frequency, and so gamma waves have a very high frequency and they typically have a very high energy because of this. Now another way that this nucleus can give off energy is in the form of particles. So the nucleus can emit an alpha particle, or it can also emit a beta particle. But particles, when they move, carry kinetic energy. And so these particles will transfer the excess energy of this nucleus away from the nucleus to make it more stable in the form of kinetic energy. So this is what we mean by nuclear instability and radioactive decay. The reason it happens is because the unstable nucleus is in a state of high potential energy. It becomes more stable, it achieves a lower potential energy condition by giving off the excess energy in the form of energy carried by a gamma wave, or energy carried by an alpha particle, or energy carried by a beta particle, or some combination thereof. It can also give off energy in the form of a neutron as well. There is such a thing as neutron radiation. But you get the picture here. It's important to understand what we mean by unstable versus stable. Now again, you've seen these terms used before in a different context in chemistry, but in chemistry, when we talk about an atom having an incomplete outer shell being unstable, it amounts to the same thing. The difference there is that we're talking about a different kind of potential energy, but it's still a system which has a high potential energy going to a system which has low potential energy. In that case, it happens by ionic bonding or covalent bonding or metallic bonding. But this is what we're talking about here in terms of nuclear radiation. So nuclear radiation is radiation emitted by an unstable nucleus. In the process of becoming more stable, it emits the excess energy in the form of energy carried by gamma waves or alpha particles or beta particles or even neutrons. Okay, so now, the radioactive decay of a particular atom within a sample of a radioactive isotope is essentially a random process. So if you have a sample of radioactive materials such as uranium, you can't predict when or if a particular atom in that sample is going to radioactively decay. They may all be unstable atoms, but the event of radioactive decay of a particular atom is spontaneous and random. But because you have so many nuclei, so many unstable nuclei within even a small sample of a radioactive isotope, we can measure a very predictable rate of radioactive decay in the overall sample. So the radioactive decay, the emission of excess energy and the change in the nucleus that occurs of any one of these atoms is random, but we can measure, for example, the characteristic half-life of a particular radioactive substance because of the characteristics of its atoms and the fact that there are so many of them. So not all elements have nuclei which are stable, as we said before. Some elements are unstable and are said to be radioactive, and they achieve stability by decaying, radioactively decaying into atoms which have more stable nuclei. So uranium, I've mentioned already, is a naturally occurring radioactive substance, and all of its isotopes are unstable and radioactive. It is the heaviest naturally occurring radioactive element. Now there are 8 other elements which are naturally radioactive. So these are polonium, astatine, radon, francium, radium, actinium, thorium and protactinium. All elements heavier than uranium are effectively man-made and are also radioactive. Plutonium is mostly man-made from uranium, but traces of this element are also found in uranium ores. So if we glance back at our periodic table, we can see that all elements heavier than uranium. And so we can see here, again, this form of the periodic table is a kind of abbreviated form. The actual form the periodic table takes looks a bit more like this. Let me just zoom out a little bit so you can see the whole thing. So the elements that have a higher relative atomic mass than uranium, these are all effectively radioactive and are largely, with the exception of plutonium, man-made elements, elements which are produced in man-made artificial processes like nuclear reactors, particle accelerators, and so on. But there are only a small number of natural radioactive elements. Okay, so let's talk about nuclear radiation in a little bit more detail. We've mentioned alpha, beta, and gamma radiation. So we need to look at the properties and the characteristics of these different kinds of nuclear radiation. So it was Henri Becquerel who first discovered radioactivity, and this was discovered effectively by accident. He was investigating the phosphorescent properties of uranium, and because he was unable to continue his experiments, he placed the photographic paper and the uranium salt that he was experimenting on with a key between them accidentally in a drawer for storage in the kind of gap that he took between doing one experiment and the next. Now, 4 days later, Becquerel looked at the photographic paper and he found that it had the image of the key on it. So you can see that here. So following further experiments to try and find out what had caused this to happen, he discovered that uranium was producing radioactivity, and for this he was awarded the Nobel Prize. Now his work was continued by the Curies, Marie and Pierre Curie, and so they spent many years studying uranium ore, which is called pitchblende. So pitchblende has the unusual property of being more radioactive than uranium. So the Curies deduced that pitchblende must contain another radioactive element. Eventually, after refining tons of pitchblende, they identified two new elements which they gave the names polonium and radium to. So, now in 1903, they, along with Becquerel, the Curies were awarded the Nobel Prize for Physics in a joint award. Now in 1911, Marie Curie was also awarded the Nobel Prize for Chemistry and became one of only two people to be awarded a Nobel Prize in two different subjects. Now, unfortunately, because of her work with radioactivity and because very little was known about the risks of radioactivity at the time, she died in 1934 of a medical condition which was almost certainly caused by working with those radioactive materials. This was called aplastic anemia, which is now known to be caused by exposure to radiation. So that's a bit of the history of where our understanding of radioactivity ultimately came from. So let's take a look at the types of radioactivity. So alpha particles we've already mentioned. An alpha particle is essentially the same as a helium nucleus. It's made up of 2 protons and 2 neutrons. A beta particle is actually a high energy, a high kinetic energy electron. It's a very fast electron which is emitted from an unstable nucleus, whereas a gamma wave is a high frequency electromagnetic wave. So these 3 different kinds of nuclear radiation, they all have different properties, and the properties that they have, the way that they behave, and the effects that they can cause are all due to exactly what makes up those types of radiation, as we'll see. So when radiation hits an atom, so when an alpha particle or a beta particle, for example, strike another atom, some of the energy from that radiation can be transferred to the atom that it hits, and this can cause an electron from the atom to be given sufficient energy to leave its energy level and escape from the atom. Now, because atoms start off electrically neutral with the same amount of protons and electrons, if you remove an electron from an atom, you're essentially creating an atom which has one more proton than it has electrons, and so this leaves the atom with a positive charge. So when an atom becomes positively or negatively charged, it is no longer referred to as an atom, it's referred to as an ion, and so this process is called ionization for that reason. Now, alpha particles, beta particles, and gamma rays have different ionizing properties. They are able to ionize atoms and also molecules to differing extents because of their differing natures. So, if we take a look at this atom here and imagine that it's struck by an alpha particle, the reason an alpha particle ionizes an atom is because as it travels past the atom, close to the atom, it electrostatically attracts its outermost electron. The electron in the highest energy level is attracted to the positive charge on the alpha particle, and as the alpha particle moves past, it strips that electron away from the atom, leaving behind a positively charged ion. Now, in contrast, a beta particle can also cause ionization, but it does so in a slightly different way. As a beta particle strikes an atom, the kinetic energy of the beta particle itself is transferred to that outermost electron. That excess energy that the electron then has allows it to leave that outermost energy level, leaving behind again a positively charged ion. Now, a gamma wave is an electromagnetic wave. So when a gamma ray collides with an atom, it is absorbed by an outermost electron, and again, the energy carried by that electromagnetic wave allows that electron to leave that outermost energy level and become free of the atom. In doing this, it creates a positively charged ion again. So the differing ionization or the different ionizing power of these we're going to talk about shortly, but the reason they ionize atoms is because of these mechanisms that we've just talked about. So again, an unstable isotope is an isotope of an element, an atom of an element, which has an excess nuclear potential energy. Sometimes these are called radioisotopes because they are radioactive. So when a radioactive element decays, it can in fact become either a different isotope of the same element or an atom of a completely different element altogether. So the original radioisotope is usually referred to as a parent nuclide. And again, this is the unstable nucleus that you start with. But the resulting isotope is referred to as the daughter nuclide. Now, many radioactive elements decay as part of a chain of decay reactions, sometimes called a decay chain, in which the original parent nuclide forms an unstable daughter nuclide which also decays, and so on. So let's take a look at an example of one of these. So this is a decay chain described which starts with a uranium-238 nucleus. The uranium-238 nucleus decays to become a uranium-234 nucleus. The thorium-234 nucleus. The thorium-234 nucleus then decays again to become a protactinium-234 nucleus, which again decays to become a uranium-234 nucleus. Now, in fact, there are another 11 stages to this chain, and it actually ends in lead-206. So let's take a look at the complete decay chain here. So this is a fairly typical decay chain, and each one of these arrows indicates the change of a nucleus to either a nucleus of a different element altogether or a nucleus of the same element but of a different isotope of that element, and this happens by either alpha decay or beta decay. So we see here this occurs by alpha decay, this occurs by beta decay, alpha decay, alpha, 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 beta, beta, alpha, beta, beta, alpha. And so lead is a stable nuclide, lead-206, and so this is stable, and so you don't get further decay after this. So we can see here that unlike in a chemical reaction where the atoms that you start with are the same atoms of the same elements that you end up with, in a nuclear reaction you may end up with atoms of a new element altogether. Now, this decay chain doesn't actually show the nuclear decay equations for each one of these steps. We're going to go into that a bit later on, probably after the 5-minute break that we're rapidly approaching. But this gives you a sense that one nuclear decay can lead to another one as long as the daughter nucleus itself is unstable. So this is what we've just seen, where one nucleus of a particular element decays to become the nucleus of a new element, of a different element. This is referred to as nuclear transmutation. So a transmutation is when one element changes into another, not due to a chemical change, which again, chemical equations, the reason you balance them is because chemical changes do not involve the nucleus. The nucleus doesn't change, and therefore the elements that you start with are the same as the elements you end up with, or the atoms of those elements. The only thing that changes in a chemical reaction or chemical change is the way that those atoms are bonded by chemical bonds, and this only involves the outer shell electrons. In nuclear reactions, it's very different. In nuclear reactions, the nuclei change, and therefore, if the nucleus changes its atomic number, you can end up and you will end up with an atom of a different element. So here's an example. When an alpha particle is fired at a nitrogen atom, the nitrogen atom is changed into oxygen and hydrogen atoms. So this would be an equation to describe that process. So we see here a nitrogen atom, a nitrogen-14 atom. We fire an alpha particle. Now, when you write nuclear equations, please don't use the alpha symbol. A lot of exam boards kind of frown on that. It's not incorrect, but it's more acceptable to most exam boards for you to write the symbol for an alpha particle as the symbol for a helium nucleus. And so we see here the alpha particle is represented by the symbol and the numbers, the mass number and the atomic number of a helium nucleus. So this side of the equation is describing the alpha particle colliding with and combining with the nitrogen-14 nucleus. This causes that combination to become highly unstable and breaks apart to form an oxygen-17 atom and a single proton, a single hydrogen nucleus. So if we have a look at this equation a bit more closely, we can see that it's not a chemical equation because the atoms of the elements that you have in the on the left hand side are different from the atoms of the elements that you have on the right hand side. However, like in a chemical process, one of the principles that you do need to adhere to is the total mass on the left hand side must be equal to the total mass on the right hand side. So we see here that the total number of atomic mass units present before the nuclear reaction takes place is 14 plus 4. The total here is 17 plus 1. So, checking the figures, we see that the total number of units of mass on the left-hand side is equal to the total number of units of mass on the right-hand side. 14 plus 4 gives 18, 17 plus 1 also gives 18. And checking also the atomic number figures, we see that these will also balance because we have 7 protons in this nucleus, we have 2 protons in this nucleus, we have 8 protons in this one, we have 1 proton here. So the number of protons on the left in total is equal to the number of protons on the right in total. So we'll come back to the idea of nuclear equations a little bit later on, perhaps in the second hour, depending on what you guys vote for. So let's have a look now at the concept of half-life. This is another one of those things that many of you asked me to go over. So half-life is defined as the time it takes for half the number of radioactive nuclei within a sample to decay. So another way of saying this is that the half-life is the time taken for the count rate from a radioactive sample to fall to half its original level. What this means is that when you are measuring count rate, you're measuring using, for example, a Geiger-Müller tube, the number of alpha and beta particles that are detected coming from a radioactive source. Now, if you start your timer and then detect using a Geiger-Müller tube how many counts per minute you're getting from a radioactive source at time 0, and then measure the time it takes for that number of counts per minute to fall by half, that is the half-life of that source. So here is a set of data from a radioactive source. So the number of counts per minute at time equals 0 was 1,000 counts per minute. So here's a question for you. I'm going to pause here and let those of you in attendance answer this either on the screen pop-up if you see it, or if you don't see that, then you can go ahead and use the chat box. What is the half-life of this radioactive source in years? Okay, so most of you have managed to get the correct answer. Well done. So if we have a look here. So if we have a look here at the graph, if we're starting at a count rate of 1,000, then the half-life will be the time that it takes for that count rate to fall to half that original level. So if the starting count rate is 1,000 counts per minute, then the half-life is the time that it will take to fall from 1,000 counts per minute to 500. So if we go to 500, read across, and we see that the half-life is 10 years. Now, this is the reason why these kinds of graphs depicting this kind of data, the count rate from a radioactive source versus time, they have this curved shape. Now, the reason for that is that the half-life is going to be the same. For example, if we start from 500 counts per minute, the time taken for it to fall to 250 counts per minute is going to again be 10 years. If it's starting at 250 counts per minute, the time taken for that to fall to half that number is again going to be 10 years. And so when we plot this as a graph, for any given radioactive source, the graph will have a similar shape to this one. Now, the half-life for a particular isotope is characteristic of that isotope. And so this can be used to, for example, identify which isotope is present in a sample. It can also be used, as we'll see, in radiocarbon dating, which is a technique which is used in archaeology to date organic remains of dead organisms. So background radiation is something that you need to be familiar with as well. So this is low-level radiation present all around us, and it comes from a variety of different sources. So we can see here the sources of background radiation and the relative proportions of background radiation that come from those sources. So we see that gases in the air make up approximately, account for approximately 33.6% of the background radiation. We also have radon from rocks like granite, which is a gas which comes from granite rocks. This makes up about 16%. This will change from one part of the country to another. And we also see from other sources as well, including from space. So I mentioned rocks. This photo from Dartmoor shows the underlying granite, which is actually common to most soft water areas in the UK. In this particular region, the limestone around this granite rock has corroded and eroded away to leave this harder granite that is usually present underneath that. So granite rocks contains small amounts of uranium, which eventually decays to release radon gas. Now, radon itself is radioactive. So areas of the country which are high in granite rocks have generally higher levels of background radiation for this reason. So the levels of radon gas in the UK are determined by the types of underlying rocks and how much of those types of rocks that you find in those regions. So this is a map showing the high to moderate levels, the moderate to low levels, and the low levels of radon found in various parts of the country. And these correspond to typically the parts of the country where you find different frequencies and densities of the kinds of rocks that release radon gas due to the radioactive decay of elements like uranium, which are found in small amounts in those rocks. So you can see here, if we have a look at Devon and Cornwall and Dartmoor, the photo that you saw in the previous slide is in this region here. We can see that the reason why we find kind of high to moderate levels of radon gas in these regions is because you have a large amount of granite rock in those regions. Now in Hampshire, we have a different type of rock, which is chalk. Now chalk comparatively contains much lower amounts of these radioactive elements, and so you get much lower levels of radon gas in these regions. So another aspect of daily life where we find background radiation is plane flights. So when we engage in air travel, we are moving higher into the atmosphere, and so there is less atmosphere, there is less gas separating us from outer space where we get radiation coming in. So we're constantly exposed to background radiation, but we can actually take action to reduce our exposure, and one of these actions is to limit the number of flights, transnational and international flights that we take per year, but also there are other things where we limit our radiation exposure. Now, we can also limit damaging radiation exposure from not nuclear radiation, but things like X-rays at the dentist. We can seal the floor of the home to prevent radon entry, and this is a common practice in parts of the country where radon gas is at higher levels. They actually use, when they build houses in those parts of the country, they use a impermeable sheet of material underneath the floor to prevent the entry of radon gas into the house. And as I've said, we can also take fewer airline flights per year to limit the amount of cosmic rays and radiation exposure from space that we get as well. Okay, so before we go into the next section where we're going to talk about the reasons for nuclear instability, and I see that that actually is the question that a lot of you have asked across the 4 or 5 different webinar, Zoom webinar rooms so far. Before we go into that, I see that we have come to the end of the first hour, so let's take a brief 5-minute break. All right, so it seems like most of you have voted across all 5 of the webinar rooms. For me to continue with the topic teaching, that's fine. Keep the questions coming as well. I see a lot of interesting questions have been asked in the Q&A panel for the 5 webinar rooms. And also, please don't forget to upvote any of the questions from other students in your Zoom room that you feel are particularly interesting or that you particularly would like me to answer. And I will be covering those questions in the last 30 minutes of this webinar in the order in which they receive votes. So it seems so far that most of those questions are concerning the exam questions from the exam questions pack. So we'll go through. We'll continue with the topic teaching, and then in the last 30 minutes or so, we'll go through those questions again in the order in which they receive votes. So keep those coming. Okay, so let's take a look at the reasons for nuclear instability. We've mentioned that radioactivity, the emission of alpha particles, beta particles, and so on from unstable nuclei occurs in order that those nuclei achieve stability. But let's take a look at the cause of instability. So firstly, one of the reasons why a nucleus may become unstable is because it has too many protons. Now typically, nuclei that have more than 82 protons will be unstable. Another reason why nuclei can become unstable is an excess atomic mass. So if a nucleus has an atomic mass of greater than 209 units, typically this will cause it to be unstable as well. Now, the third reason why a nucleus might be unstable is because of an unstable ratio of neutrons to protons in that nucleus. So this can be caused by either too many or too few neutrons in the nucleus. Now, the further reason behind, or the reasons why these things will make a nucleus unstable kind of gets into A-level and degree level territory, but if you are interested in me expanding upon that, please do go ahead and type those questions into the Q&A panel. So radioactive decay, again, is a process by which the nucleus of an atom becomes more stable. So there are 3 types of radiation that we've mentioned already. So let's take a look in a little bit more detail at the processes by which a nucleus emits an alpha, beta, or a gamma wave, and the properties of these 3 types of radiation. And if we get time, we'll go into their applications as well. So alpha radiation is formed when an unstable nucleus decays and emits an alpha particle. So again, an alpha particle is the same as a helium nucleus, in other words, a helium atom minus its 2 orbiting electrons. So it's composed of 2 protons and 2 neutrons, and so it has a relative mass of 4 units and a relative charge of 2 positive units of charge. So we can write the symbol for an alpha particle either like this, or like this. So typically, exam boards these days prefer you to use the symbol for a helium nucleus, although this again is not actually incorrect. So alpha particles have a mass of approximately 8,000 times the mass of an electron. And alpha particles are strongly ionizing because the large, slow-moving alpha particle is very likely to collide with the atoms that they as they pass through a substance. Now again, an ion is a charged atom that has become charged because it's gained electrons or has lost electrons. So the positive charge from the protons in the nucleus is not exactly cancelled out by the electrons around that nucleus. So as we saw before when we looked at ionization, as an alpha particle collides with an atom, it loses some of its energy. After many thousands of collisions, the energy of the alpha particle is low enough for electrons to attach themselves. When two electrons have attached themselves to an alpha particle, we've created one helium atom. So, alpha particles are commonly emitted from heavy nuclei which have a large number of protons and neutrons. And again, the reason for this is because those nuclei are unstable due to the large atomic mass and also perhaps because of an unstable number of a number of protons which is too high. And so they can become stable by emitting the excess mass, those 4 units of mass, as an alpha particle and also getting rid of 2 protons. So an example of this would be the nuclear decay of radium-226 by alpha emission, and this is shown by this nuclear equation here. So we're starting with an unstable metal and we're forming a more stable gas, radon, by the emission of an alpha particle. Now again, one of the common mistakes I see students making is that when they're describing nuclear decay equations, they often will put the alpha particle on the left-hand side. Now, just like with chemical equations, you need to view a nuclear equation as a before and after, an expression of what you have before versus what you have after the change takes place, and the change is represented by the arrow. And so if you're starting with an unstable nucleus and you're ending up with a more stable nucleus by giving off an alpha particle, then the alpha particle needs to appear on the right-hand side of the equation. So, in order to check that you've written the correct nuclear equation, again, we need to make sure that both the total mass number on the left-hand side is equal to the total mass number on the right-hand side, and also the total atomic number on the left-hand side is equal to the total atomic number on the right. So checking the atomic mass figures, we have 226 on the left, and we have 224 plus 4 on the right, and so this balances. Checking the atomic number figures, we find again that they balance. We have 88 on the left versus 86 plus 2 on the right. So when a radioactive atom emits an alpha particle, its mass number decreases by 4 units of mass because it's given off those 4 units as the 2 protons plus 2 neutrons of the alpha particle. Its atomic number also decreases by 2 units because again, atomic number describes the number of protons in the nucleus. If it's given off an alpha particle, it's given off 2 protons, and so its atomic number decreases by 2. And this is an example of nuclear transmutation because you end up with an atom of a different element, radon. So again, because the atomic numbers of each element are unique to those elements, then when you change the atomic number to a different atomic number, you have an atom of a different element. So if we started off with radium and we're ending up with radon, so we started with radium with an atomic number of 88, we've decreased that atomic number by 2 units, then we are dealing with an atom of a different element altogether, radon. So sometimes a decay reaction will produce another radioactive isotope which will itself decay, and we saw this in that nuclear decay chain that we saw previously in the previous hour. So thorium can become radium by alpha emission, and this is shown by this nuclear equation here. But radium, as we saw, is also a radioactive element, and so radium, this nuclide here, is also unstable. So radium can become radon by, again, alpha emission. So each step in this sequence is alpha decay, and the changing of one radioactive element progressively into others is called a decay series. Now the series stops when you form a stable nucleus. So let's take a look at beta emission now. So beta radiation consists of free high-energy electrons which are emitted from an unstable nucleus. Now, a lot of people when they're first confronted by this might be thinking, well, surely nuclei only contain protons and neutrons, so where is this electron coming from? Well, yes, there are protons and neutrons in the nucleus of an atom, but no electrons. So it may seem strange that beta particles are emitted. Now, the way that this happens is when a neutron changes into a proton and an electron, and it's that electron which is then emitted as a beta particle, and the new proton stays in the nucleus of the atom. And so the stability of a nucleus, again, is determined by, among other things, the relative proportions of neutrons and protons in that nucleus. Radioactive decay in this manner, by beta emission, changes that relative proportion by decreasing the number of neutrons by 1 and increasing the number of protons by 1, and this can make the nucleus more stable as a result. So the mass of a beta particle is negligible. The mass of an electron is effectively about 1,840th of the mass of a proton or a neutron, and so it's effectively negligible. And so the emission of a beta particle from a nucleus doesn't really change its mass significantly. So the mass number of the daughter nucleus is going to be the same as the mass number of the parent nucleus. It does change the charge of the nucleus, though, because you've gone from having a certain number of neutrons to having one less neutron and one more proton. And so the beta particle carries a relative charge of -1, and so this is emitted from the nucleus, but the number of protons in the nucleus increases by 1. So beta particles have an atomic mass of 0 and a relative charge of -1. And so again, the symbol for a beta particle can be written in two ways. We can either write it like this, where we have an electron with a mass number of 0. Now, because it is the emission of an electron from a nucleus accompanies an increase in the number of protons, the electron is considered to be the opposite of a proton, and so the atomic number of an electron in a nuclear decay equation is given the number -1. So we can either write the symbol for a beta particle like this, or we can write it like this. Now again, many examples will prefer you to use this notation. So we saw that beta radiation can also ionize atoms as well. So beta radiation, unlike alpha radiation, is moderately ionizing. Alpha radiation is highly ionizing, but beta particles are somewhat less ionizing. And the reason for this is that beta particles are much smaller than alpha particles and are therefore less likely to collide into other atoms as they pass through a sample of material. So beta radiation ionizes, as we saw before, by transferring some of its energy to outer electrons, which then have sufficient energy to leave those outermost energy levels. So when a radioactive atom emits a beta particle, its mass number remains unchanged and its atomic number increases by 1 because a neutron changes into a proton. So let's look at an example here. So carbon-14 becomes nitrogen-14 by the emission of a beta particle, and this is shown by this nuclear decay equation. So this is the parent nuclide, and this is the daughter nuclide, and the change that takes place is that the parent nuclide, the carbon-14 nucleus, gives off a beta particle, and in so doing, its atomic number increases by 1, and so if its atomic number is changing, the element is changing. We're going from carbon, which has an atomic number of 6, to nitrogen, which has an atomic number of 7. And so the daughter nucleus is a nitrogen-14 nucleus. Now, again, we need to make sure that the atomic numbers and the mass numbers on the right and the left-hand sides of the equation balance each other. And so we can see here by inspection that that is the case. We have a total of 14 mass number units on the left. We have a total of 14 on the right. And speaking in terms of atomic numbers, on the left we have a total of 6. On the right we have a total of 7 plus -1, which gives us 6. So this is beta decay or beta emission. Now, gamma rays are not particles. These are high-frequency electromagnetic waves. These have the highest frequency and the shortest wavelength of all of the 7 types of electromagnetic wave present in the electromagnetic spectrum. Now again, the electromagnetic spectrum and EM waves are something that we're going to go into in more depth in a later webinar of this series on the subject of waves. But for now, it's important to understand that gamma rays are at the high frequency or low wavelength end of the electromagnetic spectrum. And as we saw before, the amount of energy carried by an electromagnetic wave is proportional to its frequency. And so the higher the frequency, the higher the energy carried by an electromagnetic wave. And this is why the more damaging electromagnetic waves are found towards this end of the electromagnetic spectrum, where the frequencies are higher, and therefore the amount of energy carried by these waves is also higher. Now, because gamma rays are electromagnetic waves, they have zero mass and also zero charge. And so a gamma ray in a nuclear decay equation is often written like this. We have the Greek symbol gamma, and we have zero mass number and zero charge, and therefore this is equivalent to no protons. So when a gamma ray is emitted from an atom, it doesn't have any effect on either the mass number or the atomic number, but it does increase the stability of the nucleus because it reduces the energy level of that nucleus. The gamma ray itself carries energy, and so it can make that nucleus more stable by giving off some of the excess potential energy which that nucleus has, and giving it a more stable condition by giving off that difference in energy as energy carried by an electromagnetic wave, a gamma wave. So gamma rays can also ionize atoms, but they are they have the lowest ionizing power of the three types of nuclear radiation. And the reason for this is because being massless and being electromagnetic waves as opposed to particles, they are more able to pass through materials without interacting with the atoms of those materials. So when gamma rays do collide with an atom, they can ionize the atom by transferring the energy to an outermost electron. But typically they can pass through materials much more easily than alpha or beta particles. They are more penetrating. So gamma rays mostly occur as a result of alpha or beta radiation, although there are some elements that only emit gamma radiation, such as protactinium. So protactinium can give off gamma rays, and in so doing it stays as protactinium nuclei because the nuclei don't change their mass number or their atomic number. Gamma rays don't carry mass and they don't have a charge. So again, checking the atomic mass figures, we have a total of 234 units on the left and the right hand sides, and also checking the atomic number figures, we have a total of 91 units on the left and the right hand side, so those balance. So when a radioactive nucleus emits an alpha or a beta particle, the protons and the neutrons in the newly formed nucleus are often in an excited, unstable state. In this case, gamma rays can be emitted from the newly formed nuclei, and this has the effect of reducing the energy level of those nuclei even further, and thereby increasing the stability of those nuclei. So here's an example. We have a cobalt-60 nucleus here. So cobalt-60 decays by beta emission, but in addition to stabilizing the nucleus, it is further stabilized by giving off even more energy as a gamma ray. So gamma emission often will accompany beta or alpha emission in this manner. So cobalt-60 is commonly used as a gamma ray source for various applications, like for example the sterilization of food substances, radiotherapy in hospitals, and also for general use in laboratories as a gamma ray source. So I've mentioned the fact that these three different forms of nuclear radiation have various different kinds of or different abilities to penetrate materials. So let's take a look at that now. So alpha particles can be stopped by a thick piece of paper or card. Beta particles will pass through that paper or card, can also pass through skin, but will be stopped by 1 centimeter thick aluminium. Gamma rays, on the other hand, will pass through paper, through skin, through thin sheets of metal such as aluminium. They require 2 to 3 centimeters worth of lead, or even several inches of lead, in order to fully be absorbed and to fully stop gamma rays. So this gives you a sense of the penetrating power of alpha, beta, and gamma radiation. Now, The penetrating power and also the ionizing powers of these types of radiation are what determine the relative levels of risk and harm that these types of radiation will cause. Alpha particles are highly ionizing but weakly penetrating. Beta particles are moderately ionizing and moderately penetrating, and gamma rays are weakly ionizing, very weakly ionizing, but highly penetrating. So, as alpha particles have a relatively high mass and a low speed, they collide easily with the atoms of a substance. When they collide with these atoms, it prevents them from passing through a material, and so alpha particles have a very short range in air and low penetrating power. They only travel about 6 centimeters in air before the air molecules themselves will absorb those alpha particles and stop them. And they are also stopped by skin or a piece of paper. And so alpha sources of alpha radiation, are only really dangerous once they get inside your body. Your skin, the dead skin cells that form the outer layer of your skin, is a sufficient barrier to prevent alpha particles from ionizing and damaging the living cells underneath. But if you have a small piece of material which is emitting alpha particles and you inhale that and it gets lodged in your lungs, it's a different story, because once it's inside the body, the alpha particles being given off by that piece of matter are highly ionizing and can cause damage. So beta particles have a very low mass because they are effectively just electrons, and a high speed, and so they collide less easily with atoms than alpha particles when they pass through a substance. Beta particles, for the same reasons, have a greater range in air than alpha particles and are more penetrating. So they can travel up to 10 meters through the air and through some obstacles such as pieces of paper and through skin. They are stopped by about 3 millimeters thick aluminium, or slightly thicker than that. Gamma radiation, on the other hand, has no mass. It's composed of electromagnetic waves which travel at the speed of light, and so they collide very infrequently with the atoms in a substance. This means that they have both greater range in air and are considerably more penetrating through materials than alpha or beta particles are. So these can travel very, very long distances through the air. They can also go through pieces of paper and aluminium foil very easily. It requires several centimeters worth of lead or several meters thickness of concrete to stop the passage of gamma rays altogether. So another one of these properties of alpha, beta and gamma radiation that you need to be familiar with is what happens to those types of nuclear radiation as they pass through magnetic and electric fields. So here we have a horseshoe magnet which has a magnetic field between the poles of the magnet. If we pass alpha radiation through this hole in this barrier here, we'll see that the alpha particles are deflected as they pass through that field. If we pass beta particles through them, the beta particles are deflected in the opposite direction through that field, and they're also deflected through a much greater angle. Now, the reason for this is because alpha particles and beta particles are charged particles, and as charged particles move through a magnetic field, the magnetic field will exert a force on them which then causes them to change direction. But because the alpha particles have a greater mass, they have a greater momentum, they are deflected through less of an angle than the beta particles are. Now, because of the opposite charges, the alpha particles and the beta particles will experience a force in the opposite direction as they pass through the same magnetic field. Gamma rays, on the other hand, are not deflected at all because they are not charged, and therefore they don't experience any kind of force which will deflect them through a magnetic field. And so here we can see the various effects that magnetic fields will have on these three types of nuclear radiation. If we compare this to the effects of an electric field, we can see here, if we have a radioactive source embedded in a lead block with a small hole through which the radiation can pass, if we then direct a stream of those particles through an electric field, so here we have positive and negatively charged plates between which we would have an electric field, we could see that alpha particles will be deflected by that field. And again, the reasons are similar to what we saw before. The alpha particles have a positive charge, and therefore they will be repelled by the positively charged plate and attracted towards the negatively charged plate. This happens as a result of the force experienced on that positively charged alpha particle due to the lines of force, the electric field between these two plates. So the alpha particle will be deflected in this direction. A beta particle, on the other hand, will be deflected in the opposite direction because a beta particle has the opposite charge to an alpha particle. It will also be deflected through a greater angle than the alpha particle because the beta particle has less momentum, it has less mass. Gamma rays, again, are unaffected by electric fields for similar reasons to why they are not deflected by magnetic fields. They are not charged particles, they are just electromagnetic waves. So the effect of an electric field can be summarized, and also the effect of a magnetic field can be summarized in similar terms. Alpha particles are bent slightly towards the negative terminal of an electric field. Both alpha and beta particles are deflected at right angles to a magnetic field, and they move in opposite directions according to a rule which we'll explore in a later lesson or a later webinar in this series on electromagnetism. Beta particles are bent strongly towards the positive terminal of an electric field, and gamma rays are not affected by an electric field at all. Gamma rays, again, are not affected by a magnetic field either. So, one of the other things that you all asked me to cover was the uses of radiation, but actually more of the votes came in to ask me to cover radiocarbon dating and also the effects of, or rather also nuclear fission and nuclear fusion. So I will go through those in that order, but please be aware that I will make this entire presentation, the slides of this presentation that cover all of those topics, available to the attendees on the private resources page for this webinar. So if, again, to those of you in attendance, you can access that by logging into the website and then going to the first page of your webinar exam style questions pack and clicking this link here. There you will find all of the slides, including the ones that I'm not covering in this particular order, covering every aspect of this topic as well. And also bear in mind that that page will also have a live chat and also the ability for you to send me private questions all the way up to the end of your exam period in June of 2019. So please do make use of those and keep the questions coming. So let's take a look quickly at half-life, or rather radiocarbon dating, which makes use of the concept of half-life. We'll then go on to nuclear fission and nuclear fusion, but be aware that there will be slides and resources on that page for the other topics as well. Okay, so let's take a look at radiocarbon dating. So the half-life, once again, of a radioactive element, such as carbon-14, can be used to carry out radioactive dating of either organic material, in the case of radiocarbon dating, but also in geology we can use the half-life of radioactive elements found in rocks to calculate the age of those rocks. So a common form of radiodating uses an isotope called carbon-14 that we mentioned before. Now, because carbon is the basis for living, the structure of living organisms, a lot of carbon is found in the remains left after living organisms die and decay. So carbon-14 emits beta radiation and degrades, as we saw before, to nitrogen. The half-life of carbon-14 is 5,600 years. Now, all living things have roughly one carbon-14 particle in every 10 million carbon particles or carbon atoms. And so anything which is made from biological materials such as wood, for example, or tendons which were used to bind the tip of the spear to the shaft, can be radiocarbon dated. So when tested for carbon-14, for example, this ancient spear shaft had a count rate of 26 counts per minute per gram of carbon. So we can use that count rate and our knowledge of the half-life of carbon-14 to calculate the age of the spear shaft. So let's take a look at how this is done. So we can see here that the count rate that was detected corresponds to a life, or rather an age of that spear shaft of about 6,500 years old. Given that, we know that the activity rate of carbon-14 when that material was living would have been at this level. So basically, carbon-14 dating or radiocarbon dating is a way of working backwards using the decay curve of a particular element to calculate the age of that element, or how many half-lives must have elapsed for the original count rate per gram of carbon in that substance to have decayed to its current detected level. Now, I mentioned that you can also use radioactive dating not just in dating organic remains, but also dating rocks. So uranium is a naturally occurring radioactive isotope, and it's typically found in many types of rock. So the half-lives of uranium isotopes are these. So for uranium-234 has a half-life of 244,000 years, and this makes up 0.0055% of all uranium. This is its percentage abundance. Uranium-235 has a half-life of 704 million years. This makes up about 0.72% of all uranium. Uranium-238 has a half-life of 4.5 billion years, and this makes up 99.28% of all uranium. So uranium-235 and uranium-238 are typically used to date the age of rocks within which you find these radioactive isotopes. And the process is very similar to what you just saw with radiocarbon dating. We effectively use the decay curves of these elements and then work backwards by measuring the current count rate from a rock, and then working backwards to work out how old that rock must be to have reached its current count rate. So this is the way that we can date the age of the Earth. We can find the oldest rocks, and we can then date them. So we use this technique to arrive at the idea that Earth is approximately 4.56 billion years old. So natural lead, the lead found in various minerals that we find in the Earth's crust, is a mixture of 4 different lead isotopes in fairly constant proportions. Now one of these, lead-204, is not produced by radioactive decay, and this can provide a reference value for what was the original lead. So lead-204 can be used to project the original quantities of lead-206 and lead-207, the 2 uranium-lead dates obtained from uranium-235, which decays to lead-207, and uranium-238, which decays to lead-206, have different half-lives, and so if the date obtained from the 2 decays are in agreement, this adds to our confidence in the date that we've arrived at. So again, here are the count rates, or rather the half-lives for those 2 elements, and so we can use a combination of different types of dating to date various structures. For example, archaeological relics made of formerly living materials like bone and wood, and also the rocks that make up the ancient stones that make up the walls of cities, for example, around which we find those organic remains as well. So I'm not going to go into the harmful effects of radiation just yet, because the next topic within this section of GCSE Physics that you all voted for me to cover was to cover the ideas of fission and fusion. So let's go into that. Let me just find the relevant parts of my presentation here. So let's start with looking at nuclear fission first. So now, in order to understand the energy that we get from nuclear power, whether we're talking about nuclear fission reactors, nuclear weapons, whether they're fission bombs or fusion bombs, or even highly experimental technologies like nuclear fusion, we need to go to the work of Albert Einstein. So, the development of all nuclear power and weapons came about because of this famous equation, which I'm sure you've all come across, which was proposed by Albert Einstein in 1905, E equals mc squared. Now, the significance of this equation is that it tells us that a small amount of mass corresponds to a rather large amount of energy. Now, the reason for this is because of this term in the equation here, c, which stands for the speed of light. Now, the speed of light is kind of a misnomer because it actually describes the speed of all electromagnetic radiation in a vacuum, and it's approximately 300,000 kilometers per second, or in standard units, 300 million meters per second. So this term c is a constant, about approximately 300 million meters per second. Now, if you square that, obviously you're going to get an extremely large number. So if we have 1 unit of mass, 1 kilogram, in order to find out how much energy this is equivalent to, we would need to multiply that by this number here, 300 million times 300 million. So this tells us that even in a very small quantity of mass, there's an extraordinarily large amount of energy. Now, the relevance of this to nuclear fission and nuclear fusion for power generation is that when nuclear fission or nuclear fusion takes place, large amounts of energy are released as heat and light because of the conversion of relatively small quantities of mass into energy. Now, nuclear processes, nuclear reactions, release many thousands of times larger amounts of energy than conventional chemical reactions such as fuels or explosives. And so this is what makes nuclear power a viable option to replace fossil fuel power for the purposes of generating electricity. So let's take a look at nuclear fission first. So again, as we saw before, some unstable nuclei will stabilize themselves by emitting alpha, beta, or gamma radiation. But nuclear fission is a slightly different process. Nuclear fission describes taking an unstable larger nucleus and then causing it to become so unstable that it splits into 2 smaller, more stable nuclei. And this splitting is called nuclear fission. The word fission literally means splitting apart. So, uranium-235 and plutonium-239 are the elements typically used in fission nuclear reactors. They're called fissionable substances because their nuclei will readily split in half, or not in half, but into 2 smaller nuclei when hit with a neutron. So, when a neutron hits and is absorbed by a uranium-235 nucleus, it becomes an even more unstable uranium-236 nucleus. Now, this nucleus is so unstable that it immediately splits into 2 smaller, more stable nuclei, and in doing so, it releases large amounts of energy together with 2 or 3 neutrons, which then go whizzing off, which can then, as we'll see, get absorbed by even more uranium-235 nuclei, which can then repeat the process in a nuclear chain reaction. So, nuclear reactions tend to liberate and release large quantities of energy. Now, 2 main things will happen to this energy. Some of it is carried away in the form of kinetic energy of the 2 lighter nuclei because these go whizzing off away from that event. But also, some of the energy is carried in as the kinetic energies of the neutrons which are released by this process as well. Some of the energy is released in the form of electromagnetic radiation, such as light energy, heat energy, and so on. The neutrons which are released, either 2 or 3 neutrons released by the splitting of one nucleus, can then collide with other nuclei of uranium-235 or plutonium-239, whichever unstable nucleus you started with, and this causes the whole process to start again, and this can then cause that process to repeat itself in what we call a chain reaction. Now, the nuclear reaction that we're describing depends upon a neutron colliding with an atom of either uranium-235 or uranium-239, and so that collision splits that nucleus into 2 smaller atoms and large amounts of energy being released, as well as 2 or 3 neutrons, which can then go on to be absorbed by other nuclei in the surrounding area. So this can essentially cause what we call a nuclear chain reaction, and so we have a unstable nucleus being made even more unstable by absorbing a neutron which is fired at it. But that can then release more neutrons which are absorbed by more surrounding atoms, which can then cause more fission to take place. So this is the basis of the reactions that happen both in nuclear reactors in a controlled manner, but also in nuclear weapons in an uncontrolled manner. So, in order to produce the purity of uranium and plutonium isotopes which are required for nuclear reactors, they need to be purified. And this is a photograph of a uranium gas centrifuge separation plant where naturally occurring uranium is separated and purified into uranium-235, which can then be used in nuclear reactors, but also in nuclear weapons as well. So natural uranium consists mainly of uranium-238 with a small amount by weight of uranium-235, which is the isotope which is needed to carry out fission reactions. So here we can see low-grade uranium powder. It's this yellow substance, which is sometimes called uranium yellow cake. Now, enriched uranium has had its uranium-235 content increased through the process of isotope separation. And so here we can see a disk of high-grade uranium powder. Enriched uranium is a critical component of both civil and civil nuclear power generation, but also military nuclear weapons as well. So we need this kind of purity of uranium to use it in nuclear power applications, but also in nuclear weapons. In order to get this, we need to refine low-grade uranium powder by taking out the uranium-238 and isolating and purifying the uranium-235. Now, plutonium-239 is not a naturally occurring radioisotope. It's made in so-called fast breeder reactors by bombarding uranium-238 with neutrons. This produces uranium-239, which then rapidly undergoes beta decay to produce neptunium-239. Neptunium-239 then rapidly undergoes a second beta decay, which produces plutonium-239. So, the nuclear reactions which take place during the production of plutonium-239 can be summarized by this series of reactions. So, we fire a neutron at uranium-238. This produces uranium-239. Uranium-239 then undergoes beta emission to produce neptunium-239. Neptunium-239 then undergoes a second beta emission to produce plutonium-239. This plutonium-239 then needs to be chemically separated from the surrounding mixture of isotopes, and then is used to produce high purity plutonium-239 metal, which can again then be used for civil nuclear reactors, for generating electrical power, or for military nuclear weapons. So, the way that these high purity uranium and plutonium isotopes can then be used in nuclear reactors is as a heat source. So essentially what's happening is that the uranium or the plutonium in the fuel rods in the nuclear reactor is being used to generate large quantities of heat, which boils water into steam under high pressure. The steam then turns a turbine. The turbine is connected to a generator which converts the rotational kinetic energy of the turbine to electrical energy. So existing supplies of radioactive fuel are readily available and relatively easy to use, but radioactive waste is very difficult to dispose of. A release of radiation, either accidental or through more serious incidents like terrorist attacks, obviously do present a serious threat. So this is a diagram of how a nuclear reactor works. So what we have here is the primary loop. So we have a coolant, such as, for example, liquid sodium metal, which is moving through this sealed loop. Now, within this sealed loop, we have the actual fuel rods. Now, the fuel rods can be uranium fuel rods, they can be plutonium fuel rods, or they can be mixed oxide fuel rods, which are made up of oxides of the two radioactive elements. In either case, you have heat being given off by these fuel rods. That heat is absorbed by the liquid in the primary loop, and as that liquid is heated, it passes through the first loop and is then used to cool water in a secondary loop. That water is boiled to become steam. The steam then passes at high pressure through the blades of a turbine. The turbine turns and drives a generator. The generator converts the kinetic energy into electrical energy. In so doing, the steam is condensed back to a liquid and then recycled to be heated again. And so this is essentially how a nuclear reactor works. Now, the liquid in the primary loop, as well as obviously the reactor core, are highly radioactive, and so you need very thick concrete shielding around these sections of the reactor. You also need slightly less thick, but nonetheless quite thick, concrete shielding around the turbine, because the water in the secondary loop can also be radioactive over time. Now, the amount of heat energy being given off by the fuel rods needs to be controlled, because sometimes you need less power output from the nuclear power station. Sometimes you need more power output to match the demands of the national grid. And so this is achieved by control rods. Now, the control rods are made of a highly dense material which absorbs neutrons coming from the fuel rods. So let's take a look at how the control rod mechanism works. So this is a kind of zoomed in view of the reactor core. Here we can see the control rods made of boron. And so when the control rods are lowered, the neutrons being given off by the fission processes happening in these uranium fuel rods, many of those neutrons are being absorbed. This then slows down the rate of that chain reaction. But if you raise the control rods, fewer neutrons are being absorbed, being given off by one control rod and being absorbed by another. And this increases the rate of the chain reaction, which in turn increases the rate of heat output by the nuclear reactor. And so when you lower the fuel rods, you get a lower emission of heat energy. When you raise the control rods, you get a higher emission of heat energy by the reactor core. So here is a photograph of a small research reactor as viewed from the top. Here you can see the control rods, and these are raised and lowered into the reactor core using these mechanisms that you see in the photo here. So the control rods, the job of the control rods is to absorb some of the neutrons present in the reactor, which prevents them from taking part in further collisions. So this is shown here. So here we see the control rods have been lowered. These are nuclei in the uranium fuel rods between the control rods. So when the control rods are lowered, we see that some of the neutrons from each fission process are absorbed, and this allows us to control the rate of that fission reaction. Now, the disposal of nuclear waste is a problem, because the spent fuel rods, once the radioactive nuclei have decayed to an extent where they're producing less energy than is required, those fuel rods need to be replaced by a fresh set of fuel rods. But the spent fuel rods are still highly radioactive. So recent studies have suggested that the total volume of nuclear waste in the UK alone is about 500,000 cubic meters. Now this is more than enough to fill the Albert Hall 5 times over. Now on average, people in Britain live just 42 kilometers away from either a nuclear fuel or research or radioactive waste storage site. So this is a map of the UK showing the various sources of radiation in all of these different types of facilities. And as you can see here, they are distributed all the way across the mainland UK. So let's take a look at nuclear fusion now, before we go for the next break here. So nuclear fusion is thought to be the process which is responsible for the release of energy from stars. Now we're going to go into this in more depth in the last GCSE Physics webinar on the subject of space physics, but for now it's important to kind of mention it in this context. So the energy released from the Sun and other stars is thought to be due to nuclear fusion processes taking place inside those stars. Now, fusion is kind of the opposite to nuclear fission. This is the process by which the nuclei of lighter elements join together to form heavier nuclei. So in the center of the Sun, a nuclear fusion reaction is occurring at between 10 million and 15 million degrees centigrade. Now again, temperature is a measure of the average kinetic energies of particles. Now at these incredibly high temperatures, the hydrogen nuclei in the Sun are moving extremely rapidly, and when they collide with each other, they collide with such force that this overcomes the repulsion between those positively charged nuclei and allows them to join together under the influence of the nuclear forces. And so this can cause hydrogen nuclei to form helium nuclei. So hydrogen nucleus is positively charged, it's simply a single proton. When two positively charged protons come close to each other, they will repel each other with an electrostatic force because the two like charges, the two positive charges, will repel each other. But the two nuclei fuse together under these conditions because they're moving so fast that this electrostatic repulsive force is overcome. Now on Earth, nuclear fusion reactors use a form of fusion that occurs at 100 million degrees centigrade. This is 10 times the temperature of the Sun's fusion reaction. During this process, huge amounts of heat and light energy can be emitted. So, nuclear fusion reactors are still highly experimental, but essentially the original work that led to the current research into nuclear fusion began in 1932 with Mark Oliphant. Now, he discovered the hydrogen isotope tritium and found that these kinds of heavy hydrogen nuclei could be made to combine with each other. The combination of heavy hydrogen nuclei is the basis of nuclear fusion. So again, looking at our periodic table here, so if we have a look at hydrogen, we'll see that there are actually 3 different isotopes of hydrogen. By far the most common is hydrogen which only has a single proton in its nucleus. But deuterium is an isotope of hydrogen in which the nucleus of the hydrogen atom has a single neutron. So you have 1 proton plus 1 neutron gives a mass number of 2 for deuterium. Tritium is another heavy isotope of hydrogen where the nucleus has 2 neutrons and 1 proton. So Oliphant's discovery of tritium gave rise to the current search for a self-sustaining nuclear fusion reaction. So fusion reactors carry out the fusion of deuterium and tritium, the 2 hydrogen isotopes. And the idea here is to fuse these nuclei together to form a helium nucleus and in so doing release a large amount of energy plus neutrons. So this is shown by this animation here. So we have a tritium nucleus, we have a deuterium nucleus, we smash them together at high temperature and this forms a helium nucleus and a single neutron. So this is what the current so-called tokamak style of fusion reactors are attempting to achieve. It's the fusion of heavy hydrogen nuclei of these 2 isotopes of hydrogen to form a more stable helium nucleus with the emission of large quantities of energy. So at the very high temperatures required for nuclear fusion, the electrons become knocked off the tritium and deuterium atoms, and so they become an ionized gas referred to as a plasma. Now there are many other potential ways of generating the high temperatures necessary for these fusion reactions. One such method which has been explored is by using lasers. So this is a photograph of inertial fusion implosion using the NOVA laser in the US. This creates what's been described as a microsun, a tiny region of where the temperatures are comparable to those in a sun, and these temperatures can then generate the conditions necessary where those nuclei can fuse together. This is a different design of a nuclear fusion reactor. Within these so-called tokamak reactors, you have a donut-shaped chamber where you have very powerful electromagnets. The electromagnets will contain the ionized plasma and cause it to raise its temperature to the point where the nuclei will fuse together. So plasma is considered to be the 4th state of matter. Over 99% of the visible universe is composed of plasma, and this includes the material that makes up stars. Plasma TV screens, neon and fluorescent lights also contain plasma. Now, in 1954, the Zeta nuclear fusion reactors started operation at the Harwell Atomic Energy Research Establishment, and this uses an electric current inside the plasma to generate a magnetic field which compresses the plasma and produces fusion reactions. This is a photograph of the Zeta reactor releasing large electromagnetic impulses, producing the kind of lighting effects that you see here. So for nuclear fusion to take place, a substantial energy barrier has to be overcome. At large distances, nuclei will repel each other because of their similar positive charges. But if the two nuclei can be brought close enough together, this electrostatic force is overcome by nuclear forces of attraction. This force is strong enough at close distances to pull the nuclei together. A fusion reaction can sustain the fusion process if the gases can be confined at the very high temperatures necessary, and this is why we need extremely high temperatures of 100 million degrees C or thereabouts. So at these high temperatures, the gases produced again are referred to as plasmas. They are gases within which the atoms have lost their outer shell electrons and are simply positively charged nuclei. Now, to maintain and confine that plasma at these kinds of high temperatures, the plasma is confined inside a donut-shaped, toroidal-shaped magnetic field. Fusion reactors like this are important because fusion reactions release much larger quantities of energy than nuclear reactions, and also a benefit of fusion power is that unlike fission-based reactor designs, these reactors do not produce highly radioactive waste materials. Now, another more unfortunate application of nuclear technology is obviously nuclear weapons. Now, there are two basic types of nuclear weapons that have been developed. One of them is based on fission, and one of them is based on fusion. The first weapons produce the explosive energy through nuclear fission reactions alone, using either uranium or plutonium. These were referred to as the atomic bombs. Now, there is a second generation of nuclear weapons called the so-called hydrogen bomb. Now, these use conventional fission nuclear explosives around a heavy hydrogen core. So you have a core within which you have pressurized heavy hydrogen isotopes. Around that core, you have several fission bombs which explode simultaneously to compress the hydrogen in that core to the temperatures and the pressures required to initiate a fusion reaction. So fusion bombs can be thousands of times more powerful than fission bombs. These are the bombs typically referred to as hydrogen bombs. Okay, everyone, looks like we've come to the end of the second hour, so I'm going to go for another 5-minute break. Again, at the end of this 5-minute break, you will be presented, those of you in attendance, with the option of extending this webinar by an extra 30 minutes before we go into the Q&A section. Whether you choose to do that or not, we will go into the Q&A section in the last half hour, where I will answer the questions that have been asked in the Q&A panels for the 5 Zoom webinar rooms. I'm going to be going through those in the order in which they received votes. At the moment, it appears that questions concerning the exam questions in the exam question pack are receiving the highest number of votes. But in any case, let's go for a 5-minute break, and then you can vote as to whether we continue by half an hour or whether we go into the Q&A segment. So I'll see you in 5 minutes' time. All right, so it's pretty unanimous. It seems like you've all asked for me to go straight into the Q&A. That's fine. Now, having a look across the Q&A panels for the Zoom rooms for the 4 schools which are in attendance and also the private students' Zoom room, it seems like the vast majority of the votes have been given to questions relating to the exam questions. In particular, it appears that question number 4 in your exam questions pack seems to be the one that you all want me to, not all, but certainly the majority of you want me to go through. So let's take a look at that. Now, again, I will be uploading the complete mark scheme for all of the exam questions in this in your exam question pack to the private resources area, so please do check up on that. And even after this webinar concludes, if you do have any questions about any of these exam style questions or any of the topics that we've covered in this webinar, or any other topics relating to atomic structure and radioactivity, please do go ahead and either type your questions into the live chat on that page, or if you'd prefer to send me your questions privately, then you can use the private messaging function on that page as well. And whether your question is asked via the private message or the live chat, I will typically respond within 24 to 48 hours. Okay, so let's take a look at question number 4 here. Where is it? Yeah, so question number 4. All right, so atoms are different sizes. One of the heaviest naturally occurring stable elements is lead. 2 of its isotopes are lead-206 and lead-208. So they're giving you the mass numbers and atomic numbers of these 2 lead isotopes. So what is meant by the term isotopes? And they're giving you 2 marks for this, and they're also giving you 4 lines on which to write your answer. So in keeping with good exam technique, you should expect that if you're being given 2 marks for this, you should expect to make 2 logical points. And you should also use the amount of space being given for your answers as a general guideline as to how much you should be writing for these answers. So now this is another one of those cases where I'm going to repeat one of my mantras. Memorize not just your equations, but also the definitions for the key terms, because a lot of marks are available in exams for simply being able to write down the correct definitions for things. So a very easy, simple way of writing down the definition for the term isotope is to say that isotopes of an element are atoms of the same element with different Now, you can say different numbers of neutrons, or you can say different mass numbers. So I'm just going to go ahead and say different numbers of neutrons. Numbers of neutrons. So isotopes are atoms of the same element with different numbers of neutrons or different mass numbers. So if you would have written down atoms of the same element, that would get you the first mark. Different numbers of neutrons, that would get you the second mark. You could also say, instead of atoms of the same element, because atoms of the same element have the same atomic number, you could have said atoms with the same atomic number or the same number of protons. But in either case, that would get you the 2 marks. So this part of the question, I don't think presented too many of you with too many problems. I think it's the later parts of this question. So let's go through those. So how many protons are there in the nucleus of a lead-206 atom? Well, again, atomic number of lead is 82, and again, you will be given either the information about the element in this form or some section or the whole periodic table from which to look up this information. So number of protons in the nucleus of a lead-82 atom corresponds to the atomic number, so it's simply 82. Number of neutrons in the nucleus of a lead-206 atom, well, the mass number of a particular isotope is the total number of neutrons plus protons. And so if you have 206, so mass number is number of protons plus neutrons, excuse me, plus neutrons. So if this is equal to 206, but the number of protons is 82, then the number of neutrons is going to be 206 minus 82. And so if ever you want to find the number of neutrons in the nucleus of an atom, you can simply subtract the number of protons, the atomic number, from the mass number. And this gives us 124 neutrons. So a nucleus can be accelerated in a particle accelerator and directed at a large nucleus. This produces a heavy nucleus that will decay after a short period of time. This is shown in figure 1. So we have a nucleus, we have a large nucleus, and we have a heavy nucleus. Now, this is an example of a question which is presenting you with a context that you're probably unfamiliar with. your specification probably doesn't have anything to do with particle accelerators in it, or very little. And yet the examiner is asking you about particle accelerators. Now, this is a typical trick that examiners will use in order to put you in an unfamiliar context, but they're doing it so that you can apply your existing understanding of this topic to this unfamiliar context and then answer the question. So, in 1984, nuclei of iron were directed at nuclei of lead. This produced nuclei of hassium. Complete the equation for this reaction by writing numbers in the empty boxes. So, as with any question, you need to first of all take a look at the stem of the question, which is presenting you with the context, and ideally underline or highlight the various parts of that stem which might be relevant. So, this is the general case. A nucleus can be accelerated at a larger nucleus to produce a heavier nucleus. Now, the aspect of your learning that should spring to mind here is the idea that nuclei can absorb the other nuclei. So we already saw what happens when a nucleus absorbs a neutron. It becomes a larger nucleus. So here we're starting with a smaller nucleus, and it's being absorbed by another nucleus to produce a larger nucleus here. And they're even giving you a diagram to illustrate this principle here. So complete the equation for this reaction by writing mass numbers in the empty boxes. So, or writing numbers in the empty boxes. So iron is 58. We don't know what the atomic number of iron is. We don't know what the mass number of this lead isotope is, and we're being given a space for the atomic number. Now, if it's lead, then the atomic number will simply be the atomic number of lead, which is 82. So we can start straight away by writing 82 here. We also know that the atomic numbers on the left and the right hand sides of a nuclear equation are going to be equal. The total atomic number on this side must be equal to the total atomic number on that side. And so if we have 108 on this side, then we must have a total of 108 on this side. So 108 minus 82 will give us the atomic number of iron. Now, in a physics exam, you will not be given a periodic table, generally speaking. And so we're calculating the atomic number here rather than just looking it up in a periodic table. But again, it's fairly straightforward if you remember the principle that we saw earlier on, where the total atomic number on the left and the right hand side must be equal to the total atomic number on the right. The total on the left must be equal to the total on the right. So we have a total of 108 here. So 82 plus something makes 108. So 108 minus 82 is 26. So this is 26. Now, the other thing is the total mass number on the left side of the equation must be equal to the total mass number on the right. So on the right, we have this mystery particle, X. But that particle has a mass number of 1 and an atomic number of 0. So on the left, the total must be equal to 265 plus 1. 265 plus 1 is 266, and therefore the mass number of this lead isotope must be equal to 266 minus 58, and so that gives us 208. So this is a lead 208 nucleus, and this gives you the 3 marks. 1 mark for this, 1 mark for that, 1 mark for that. 3 marks. So the next part of this question, use the correct answer. Let me go back up a little bit. Use the correct answer from the box to complete the following sentence. Particle X in part B, part 1 is an electron, a proton, or a neutron. Well, again, using the notation that we've come across already, a neutron is a particle with a mass number of 1. But if this was a proton, then the atomic number would be 1. And it's not. It's 0, so it can't be a proton. If it was an electron, again, going back to the notation that you saw before, the electron is represented like this. It's equivalent to minus 1 proton. And so it can't be an electron. It must be a neutron. So, correct answer here is a neutron. Okay, part 3. After acceleration, the iron nuclei travel at a steady speed. So let's highlight the parts of the question that might be relevant. Again, this is good exam technique. Highlight or underline the information given by the question which may be relevant to the answer, and also any values you're being given for variables or for quantities in the question. So we have a steady speed, 1/10 the speed of light. We're being given a value for the speed of light, 3 times 10 to the 8th meters per second. We're being asked to calculate the time taken, and we're being given the distance traveled, 12,000 meters. So once you've got those quantities, once you have highlighted or underlined or made note of the quantities that you're being given in the question, you can then go on to identify which equation contains those quantities. So we have a steady speed, so whatever equation we're going to use needs to be regarding a steady speed, a constant speed. We're being given the speed of light, speed. We're being asked to calculate the time taken, and we're being given a distance traveled. So given the fact that we have speed, distance, and time, the equation that should spring to mind, which is what you need to write down, always show the examiner which equation you're using. Speed is equal to distance divided by time. We're trying to work out time, so we need to rearrange this equation to make time the subject. We multiply both sides by t to get Vt is equal to d. And then we divide both sides by v to get t equals distance divided by speed. Now the speed we're being given is this, but the nuclei are traveling at a steady speed of 1/10 of this speed. So the speed is going to be 1/10 of this speed. 1/10 of this speed is 3 times 10 to the 7th. So this is 3 times 10 to the power 7 meters per second. And so now we can substitute our value for the speed of the nucleus, our value for the distance traveled by the nucleus, into this equation. So we have the time taken is going to be 12,000 meters divided by 3 times 10 to the power 7, which if we type those values into our calculator here, 12,000 meters divided by 3 times 10 to the power 7 is 0.0004 seconds. So 4 times 10 to the power minus 4. Minus 4 seconds. So this is a 2-mark question, and yes, I'm somewhat belaboring the point about how to go about this, but I'm trying to get you guys into the habit of approaching these calculation questions in a certain systematic, methodical, logical manner, showing every step in your reasoning and your working. Now obviously there's only 2 marks available for this question, but part of the reason that it's valuable to approach questions in this way is that it develops good habits. It also means that when you've got a little bit of time towards the end of the exam, where you have finished the exam, you've got a little bit of time left over, you can go back through your answers to your questions. When you lay out your reasoning in this manner, it's much clearer what you're doing, so that you can more easily spot any errors that you're making in your calculations in that critical period when you're going back through your calculations. So in this question, part 3, we're being given 2 marks, 1 mark for the working and 1 mark for the correct answer here. 2 marks. Part 4, linear accelerators in which particles are accelerated in a straight line are not used for these experiments. Circular particle accelerators are used. Suggest why. Now, this goes back to another point of exam technique. Again, in this question, you're being presented with an unfamiliar context, a context within which you've probably never been taught about linear accelerators or things like that, or very little about them in your course, so you're unfamiliar with them, but the examiner is requiring you to apply your existing knowledge to this situation in order to solve the question. So this is another reason why you'll see often this command word appear in these types of questions which present you with unfamiliar contexts. It doesn't say explain why, because the examiner is aware that this is a context which is probably unfamiliar to you, somewhat unfamiliar. It's saying suggest. Suggest means use the information in the question with which we're aware that you may be unfamiliar, and your existing knowledge to give a reasonable best guess or educated guess as to why. So linear accelerators, these accelerate particles in a straight line, but these are not used. Circular particle accelerators are used instead. Now, the reason for this is that the particles need to travel a very large distance. So you already know in the stem of the previous question that the particle is traveling 12,000 meters. That's 12 kilometers. So if you used a linear accelerator, the equipment would have to be extremely long. It would need to be 12 kilometers long. It would occupy a very large space, which may not be practical or feasible. So you can take a circular path and accommodate that same distance in a much smaller space, requiring much less of a kind of footprint for the equipment. And so there's 3 marks available. Now, another point of exam technique that you need to pay attention to, many of you are already familiar with the idea that you need to be using the number of marks available as a guideline in questions where you're being asked to suggest or describe or explain or even calculate how much detail or how many points you need to make in order to get those 3 marks. Yes, you need to make 3 logical points here in order to get the marks, but also the amount of space you're being given by the examiner should also provide you with a clue as to how much detail you need to give. So here we can say that particles need to travel a long distance. So in the previous example, we saw 12 kilometers required. So that's the first logical point. The second point that follows on from that is that you would need very large, or the equipment would need to be very long. So therefore, a large amount of space is required, or large amount of space is required if the path of the particles is linear. I.e., equipment would need to be very long. Now, so that point follows from the previous point. This is the way you need to construct your answers. It needs to be a series of statements, each of which logically follows from the preceding statement. So now that we've said this, we can now give a suggestion as to why a circular particle accelerator is used instead of a linear one. A circular path takes up less space requires less equipment, or requires smaller equipment for the same path length. Obviously you can word these in various ways, but this will get you the 3 marks. 1 mark for this statement, 1 mark for the statement that follows that, and the 3rd mark for the final statement giving the suggestion. 3 marks. Okay, so let's move on to the next part here. So Hassium-265. Now again, before I go any further, you'll notice that this isotope was mentioned in the very beginning of the question. Or rather, in the first part of the first couple of parts of the question, you see here, in a previous part of the same question, we have Hassium being mentioned, and it's even present in this nuclear equation, but it wasn't specifically referenced in this part of the question. One of the mistakes that I see people making is that they'll read this question, but they'll forget that this was mentioned in a previous part of the question. Now, it may not be relevant to this answer, but frequently students will drop marks or make mistakes because they've forgotten that the information that's relevant to answering the question that they're answering at that particular moment in time is not present in the stem of that part of the question, but is present in a previous part of the question. As you work through these multi-part questions, don't lose track of the information that was given to you in earlier parts of the question. It can be relevant, and I see students making this mistake quite frequently. And again, this happens not because the student is, not a good student. It's because in the heat of battle in an exam, sometimes you forget, you kind of home in on what's in front of you in that part of the question, and you may miss out on key information that was mentioned in previous parts of that question. So, Hassium-265 decays by alpha emission with a half-life of 0.002 seconds. What is meant by half-life? So tick 2 boxes. So the average time for the number of nuclei to halve, the time for the count rate to be equal to the background count, the time for the background count to halve, or the time for the count rate to halve. So in this part of the question, it's the average time for the nuclei to halve, because again, it's if you take 2 samples of the same radioactive material, they may have slightly different measured half-lives, but if you take many samples of that radioactive material and you measure the average time for the count rate to halve, that's a more precise measurement of the half-life of that particular isotope. So the first one would be this, and also it's the time for the count rate to halve. So it's the time for the count rate to halve, but it's also the time taken for the number of radioactive nuclei in a sample to halve. So both of these are components of the definition of the term half-life, which is again a good reason or a good reminder that of the importance of memorizing the formal definitions for these key scientific terms. So 2 marks for that one. So complete the equation for the decay of Hassium-265 by writing numbers in the empty boxes. So here we have Hassium-265, and we see that it's decaying to a different element here. Again, we're being told, we're not being given a periodic table where we can simply look up the atomic number of this element, where we're having to deduce it by knowing that we have an alpha particle being given off. So we know that an alpha particle has a mass number of 4 and an atomic number of 2, and we also know that the total mass number on the left-hand side of this equation must equal the total mass number on the right. We also know that the total atomic number on the left-hand side of this equation must equal to the total atomic number on the right. And so the mass number of this element must be this 265 minus 4. So this mass number is 261. We also know, for similar reasons, that the atomic number of this element must be equal to this atomic number minus 2, and so this gives us an atomic number of 106. So that would get you the 2 marks. So 2 marks, 1 for the correct numbers here, and 1 for the correct numbers here. So part D. The table below shows how the atomic radius of some atoms varies with atomic number. And we're being given those atomic numbers and also the atomic radius in picometers. Now 1 picometer is 1 times 10 to the power minus 12 of a meter. On figure 2, the graph, use the data from the table to plot a graph of atomic radius against the atomic number and draw a line of best fit. So they've plotted 2 atomic numbers for you. So we see here the graph. Now, when you're presented with a graph like this, please pay attention to the increments. So here we have from 0 to 20, we have 10 increments on the horizontal axis, which means each one of these increments represents 2 units. Excuse me, 2 units of atomic number. Here we have 20 units between 50 and 100. So we need to take account of these increments before we start plotting points, and it's a similar principle when we are constructing a graph from scratch. We need to make sure that we choose increments which are relevant to the range of our axes as well. So let's take a look at how we would go about it. Okay, so given that we have 20 small increments between 50 and 100. That makes each one of these small increments on the vertical axis worth 2.5 picometers. So one small increment on the y-axis, on the vertical axis, is equal to 2.5 times 10 to the power minus 12 meters, 2.5 picometers. On the horizontal axis, as we saw, we have from 0 to 20 is 10 small increments, and so on the horizontal axis, one small increment corresponds to 2 units of atomic number. 2 units of atomic number. So now we can start to plot our points based upon this information here. So we have here the first 2 points are already plotted for us. So the point for atomic number 15 and the point for atomic number 35 are plotted at 100 and 115 picometers respectively. The next one is 50 units of atomic number and 130 picometers. So here we have from 40 to 60, 10 units of atomic number, 20 units of atomic number, so 50 would be in the middle. So 1, 2, 3, 4, 5. This is our middle point. And so this would be the point where we need to look at the horizontal axis here. 5 units corresponding to 10 atomic number units. So this is where we have 50. And the atomic radius is 130. Now 130, 30 units here, is needs to be plotted given that each one of these is 2.5. So if you need to work that out, you can take 30 units divided by 2.5 is 12. 12 small units above the 100. So if we follow this line up here to where it crosses the axis for 100, which is here, just line it up with my eye here, going blind, staring at this monitor. There we go. So 13 units above this point. So here we would have 1 unit, 2 units, 3 units, 4 units, 5 units, 6 units, 7 units, 8 units, 9 units, 10 units, 11 units, 12 units, 13 units. So we need to plot the points in this manner. So again, in the interest of time, I'm not going to plot these units one by one because, to be honest, this part of graph plotting, it's just a repetitive exercise. I don't want to use up too much more of the time left for this Q&A segment here, but that's how you do it. Now, scientists believe that the element with atomic number 126 can be produced and that it will be stable. Use your graph to predict the atomic radius of an atom with atomic number 126. Now, the way that you would do that is once you have drawn your line of best fit, whatever that line of best fit may be, you would need to then read off 126 here. So 246 you would read off here. Let me just mark that here. 126 units would be here, and then you look at where the vertical line from here upwards crosses your line of best fit, and then read across horizontally and read the number on the vertical axis, the atomic radius in picometers. But again, all of this is based upon you being able to identify what is the small increment and then read off accordingly. Now, questions like this typically will allow a certain amount of leeway because, again, not everybody is going to plot absolutely everything absolutely perfectly, but a general guideline is all of the points that you plot on a graph in an exam question need to be accurate to within 1/2 of one of these squares. Now, there's a couple of questions in this exam question pack which require you to plot graphs and to then draw lines of best fit against which you then make measurements to solve questions like this. Really, you need to get good enough at that to be able to plot the points accurately to within 1/2 a square, but also to do so relatively quickly. In exam questions, you should be aiming at no more than 1 minute per mark. So if you've got a point plotting question like this one, within 2 minutes, you need to identify the correct increment for the vertical and y-axes. You then need to use those increments to accurately plot within 1/2 of a square each one of the points and then draw a good line of best fit. Now, that may seem like a lot to do, and to some extent it is, but it's really just about developing that procedure that I've just described to the point where you're able to do it relatively quickly. I will again upload the mark scheme to this whole exam paper, including the parts that we haven't gotten to, or these exam style questions. But there are a couple of questions here where you're required to plot graphs. And so I will include an upload form on that private resources page where you guys can upload images of the graphs that you've plotted, and I'll comment and feedback on those for you. But that it really is a very key skill. Now, unfortunately, modern maths, GCSE maths specifications unfortunately don't require your maths teachers to teach you to be particularly good at plotting graphs or reading graphs. That is unfortunate. I teach maths as well, so I know very well that that is the case. However, science does require you to be very, very good at plotting graphs and reading from those graphs. And so if you need any further help with that, then please, by all means, go to the private resources page and ask any questions along those lines that you have on this topic. And this is a theme that we're going to be covering in a lot of the other webinars as well, and that does appear in the exam style questions packs for those webinars. So again, those of you who have attended and will attend those webinars, you will be able to ask me questions about those relevant questions in the packs and graphs and things like that on the private resources pages there as well. Alright guys, so it seems like we've come to the end of this revision webinar. Thank you to all of you who are in attendance for taking part. Please do make use of the live chat and the private messaging function on the webinar resources page. I will respond to your questions there all the way up to your final exams. I'm there to help you. But until the next webinar, take care of yourselves, and I'll see you in the next one.